Hey, so in chapter 9, what we're going to be talking about is population means and how we can estimate them. So in chapter 8, just to remind you, what we were doing is that we were trying to use a sample to compare to a population percentage, which we called P. Okay? So in chapter 9, what we're going to be doing is that we're going to be trying to use a sample to estimate a population's mean, which we're going to call mu. So a lot of the vocabulary is going to be the same from what we talked about before. So remember, when we're looking at our sample, which is the thing we're trying to use to estimate our population, the sample mean is going to be x bar, and the population mean is going to be mu. The sample standard deviation is going to be s, and the population standard deviation is supposed to be sigma. We're not going to worry about variance. The sample proportion is p hat, remember that's the percentage, and the population proportion is p. So, for example, in chapter 9, what we're going to be doing is we're going to be looking at averages of a population and seeing how well our sample does of trying to estimate that average. So, in this example, we have a normal distribution of 7,128 runners from a marathon. So that is going to be our population. So this and this are our populations. Okay, so what we do is that we randomly take a sample of 30 runners from that 7,128, and we find that of those 30, if we add all of their finishing times up and divide it by 30, we're going to get an average finishing time of 95.1 minutes. So what we're going to do is that we're going to repeat this over and over and over again, and we're going to plot that on a chart. So just keep in mind that we're trying to say something about this population using a sample of 30. And in this one case, we had a sample of 30 return 95.1 for average. Now when we do that over and over, notice if we randomly sample all of these runners, what's going to happen is that we're going to have some groups that are a little bit slower. So here we have 30 runners whose average was about 100 minutes. But here it looks like we had a couple of fast runners or faster runners, and their finishing time was about 80 minutes. Now here's the deal. Typically, any group of 30 will have some fast and some slow, but remember, we're not looking at their individual times, we're looking at their average times, so we're adding them all together. And when we do that, we can see that most of our samples, look at all those dots grouped together, are going to average out to 91 minutes, which is the same as our population. So if we repeat this process over and over and over again, what we see is if we increase the sample size, okay, so over here what we had is that we had our samples run between about 80 to 100. And here you can see that distance is getting smaller and smaller and smaller and more grouped around 91. Again, because the more observations you have in your sample, the more you're likely to have a slow runner, even out a fast runner, and etc. So what we notice is that as the number of samples increase, our precisions increase. As well, since we're doing all of this randomly, what that means is that our method is going to be unbiased. Okay, so what that means is that we're not just interviewing people towards the end of the race so that we would get some means that were too high or some means that were too low. So this is going to be the same as chapter 8, except for the formulas are going to be a little bit different. So again, we still expect our samples average to be about the same as our population average, but what do we expect it to be off by? It's going to be off by what? So what's the error we expect to be off by? Well, the error, the standard error, is actually much simpler in this chapter than it was in the last chapter. It's going to be your sample standard deviation divided by the square root of your sample size. So let's look at an example. Suppose a person's MP3 player, just so you guys know, that used to be a little tiny thing that we played music on that we downloaded from our computers, has a mean song time of 273 seconds and a standard distribution of 84 seconds. That is, it's a right-skewed histogram, and what we do is that we randomly create a playlist of 30 songs. So the first question is that 273 a parameter or a statistic? Well, since it comes from all of the songs that we're looking at, that is going to be our parameter. Remember, parameter comes from population, statistic comes from our sample. All right, so if we take a sample of 30 songs, randomly, what can we expect the average length to be? Well, since we took them randomly, that means that it's unbiased, so we can assume that the average playtime of these 30 songs is going to be the same as the average playtime for all of the songs, so 273. Now the standard error in this case is going to be 84 divided by the square root of 30, which will round to 2 decimal places. We're going to get 15.34 seconds. So here's what that means, is that if we take 30 random songs from our playlist, we expect that if we add all of their playtimes together and divide by 30, that is, take the average, we expect the average playtime to be around 273 minutes, but we're probably going to be off by a little bit, right? So how much are we going to be off by? We're going to be off by probably 15.34 seconds. Let's do one more example. So, baby elephants, yes, I love them, have an average weight of 221.3 pounds, and they have a standard distribution of 68 pounds. What we do is that we randomly select 23 baby elephants from our sample. Again, what do we expect the average weight of these 23 baby elephants to be? Well, since we collected them randomly, we expect our sample to have an average very similar to our population. Now, what's the standard error? Well, we don't expect them to be exactly the same as our population, but we expect them to be pretty close. So, for our standard error, that's going to be 68 divided by the square root of 23. And again, let's just go ahead and round that to 4 decimal places. So what we end up getting is 14.18. So again, the verbal interpretation of this is that if we take 23 randomly sampled babies from our population, we expect the average of their weights to be the same as the population, so about 221.3, and we expect that to be off by 14.18 pounds.